I come back. Lynn, yes.
Using both, right? Yeah. Because in radiometric there will not be spectral
But I'm afraid I've not understood your question. So you're asking what type of information we are using here. Depends on what you put into a classifier. Let me go back a couple of slides. Here you have your data, which contains different information. So it's spectral, spatial, and radiometric information. The simplest approach is leveraging spectral classification, which is what we have discussed earlier. So I built my previous discussion, on the assumption that we will be leveraging spectral information, okay? Because that is the most straightforward way of conducting this discussion. But when I say similarity of behavior here, typical behavior of pixels, okay, I do not necessarily mean that it needs to be spectral. It is generally spectral when you're using multispectral data or hyperspectral data. But in all cases, you can also decide you want to leverage spatial information. So now, since you asked, I was about to discuss it at a later stage. But remember the discussion on speckle noise. Okay, so we have an image here derived from a radar data set of a rural area where you can clearly see the speckle noise. This is a JPEG, okay, so it's ugly, but still you can visually assess that you're in the presence of speckle noise. Does that make sense? And here you have no spectral information at all. How can you classify based on the information content of this? For sure, you cannot use spectral information, which you don't have, but you can still use spatial information. So, for example, what is this spatial information? It can take the form of local statistics. Like, for example, I take a pixel and I take its immediate neighborhood. How are placed these values? How does the central value relate to the others? Because this will tell us something, will help us distinguish between this parcel and this parcel. Because in this parcel, I will likely find around, even if I have a dark pixel, around it I will find a certain number of bright pixels, which will not happen here. Okay. This is spatial information, spatial and radiometric information. The way I can do that factually is, since classifiers always expect a multivariate vector. Okay, so the input of the typical classifier is a multivariate vector. It can be also a matrix in some cases, but it's something that conveys multiple numbers. If these multiple numbers represent the spectral response of the sample, then you're classifying based on the spectral information. But if these numbers contain spatial information, like, for example, as I said, the average the value of the pixel and the average of the pixels next to it. And then possibly also the average of the outer ring of pixels, etc. You have multiple numbers, so you're building a vector which conveys spatial information, because it's not spectral, it's not radiometric, it's something you're considering the relationship between that pixel and the nearby pixel. That's also a vector that a typical classification algorithm can understand, and you can use that to carry out classification. Okay, so in this sense, it's not what you input into a classifier or what your classifier leverages is not necessarily spectral information. Okay. Okay. So, as I said before, closing our previous lecture, generally the classic approaches to classification define an approach which is obviously dependent on the data that you use, especially if you're using unsupervised classification. But somehow they do not modify their behavior based on the data. Okay. So, for example, for the k-means, the data that you input is iteratively used to tune the center of the clusters, but the behavior of the classifier is always the same. In maximum likelihood, the training process only involves defining the statistics of defining the parameters of the Gaussian and writing these parameters into the classification algorithm. But there are other approaches that came up at a later stage, which are called machine learning. Machine learning basically means that the algorithm learns increasingly from the data. Okay, this is a very, very general statement. Okay, so it includes very basic approaches like decision trees, which we are about to see, and also much more complex and costly approaches like deep learning. Okay. So the classical example of machine learning is called decision tree, which is a supervised learning technique where you basically start from, for each sample, you start from a root decision node, and this sample will be assessed by an algorithm which will decide whether you are in this case or in this case. And then, if you are in this case, you will have a second look at the data, and you will take a more refined decision, and then again and again and again. I think I don't need to explain it to you because most of you will know about decision tree, right? Okay. So this is machine learning because in some way or another, you will have to design this tree. You will have to define what decisions are to be taken based on what. And so that is the subject of learning, because prior to the use of this tree, there will be a learning step where the samples will be used with a strategy like, for example, classification and regression tree, where you take the data, you try to cut it in two, and you use your training data to determine whether your random cut has actually separated something from something else in a relevant manner. If so, okay, then you move on to defining the next split on each of the two subsets. If not, you try again, etc., etc. This is learning because you build incrementally a decision strategy. Okay? Whereas, for example, in the maximum likelihood approach, in the maximum likelihood classifier, you don't learn incrementally. You simply take the parameters of the Gaussian and you input them into the classifier, and that's it. Okay? So there's not really much, but this is an example of a decision tree that I took from classification, so from a scientific paper, which can be used to give you an idea of how a decision tree is used in Earth observation. I can take band 4, because this is interesting because it mentions specific bands of Sentinel which have a specific meaning. So now, like B4, so this is the root. Naturally, what you don't see here is that there has been a step prior to the tree where samples from a given area, labeled samples from a given area, were used, were applied the CART to them, and it came up with this tree structure. B4, as you may remember from our exercises, B4 stands for red. 2, 3, 4 are the bands which relate to blue, green, red, respectively. So B4 is red. And note that beneath a certain value, you go to this node, and above same value, you go to this other node. And there you take a new piece of information, a new piece of data. You have used before, B4, so you have consumed your piece of sample. Now you move on to something else, something that you have not used previously. So B4 is red. Why did I point this out? Because, you see, when it is smaller than a certain amount, one of the options that you get right after the following node is agriculture. Why is agriculture there? This is something that was learned automatically by the CAR3 algorithm. Why did it place agriculture there, meaning vegetation there? Why is it under this node and not under this node? What band is this? Red. Yeah, you're using spectral. I agree with you, you're using spectral. Well, it's spectral and radiometric information, because actually what you're assessing here is radiometric. Okay, so greater than or smaller than on a certain band, it's radiometric information. But upstream of that, there's a decision of using band 4. The decision of using band 4 is spectral. It's not radiometric, okay, because you're pointing out at a certain lambda interval. That lambda interval is significant, helps you answer this question, because what is the spectral behavior of vegetation? When we say agriculture, we mean vegetation. They made a poor selection of classes, because agriculture can be a lot of different things. Let's assume they meant vegetation. Okay. If you say agriculture, you're generating trouble, because agriculture is a land use class, not a land cover class. Okay. Let's fall back to land cover class. Remember, land use is one thing, land cover is another thing, and if you aim directly at land use, you're seeking trouble. Now, let's say it's vegetation. B2 can be any, but in this case, we have agriculture. B4 is red. What is the behavior of vegetation in band red? Yes, it absorbs, right. Chlorophyll. Band 4 reacts weakly because vegetation, because the chlorophyll in green vegetation sucks all the, not all, but almost all the incident radiation. So when you have vegetation, you expect a weak response in band red, which in this case is band 4. Okay. So we find vegetation on this branch of the tree and not on this branch of the tree, because that's what you expect from vegetation. And notice that we did not put it there ourselves. It was found automatically, it was decided automatically during the learning process. Okay. But what we have done now is a very interesting step, which is called the explanation of the classification strategy. You know, there's a lot of files on explainable deep learning, right? Explainable. Why explainable? Because you need to be able to report on why a certain decision was taken. Okay. This is machine learning. This is not deep learning, but it is explainable. Okay, so one big advantage of the decision tree as a classification strategy, at least in remote sensing, is that if you know the matter, if you know the insights of the data that you're looking at, you can explain why certain decisions were defined. Okay. So I wanted to point this out because I think it can be interesting for you. What else? Fallow water. Well, I think this is the most interesting point. But if you walk down the tree, you see that other bands are used. In some cases, you also reuse the same band when the machine realizes that, after all, there's still something that band can tell. So before, for example, if it's smaller than 59, then you go to filter node. If it's greater, then you go to water. This is a little bit surprising to me because water tends to be dark, so it tends to have low values, and in fact, you find it again here. But in general, I mean, if you know the spectral behavior of the length cover classes that you intend to separate, and you look at the tree, you can explain it. It's not like a deep learning network where you put everything in and you get a response and you don't know where that response comes from. This is completely different. Okay. Yes. What is?
Water is found after B4 there, again after B7, and again after B1.
Yeah. So because. Yeah. I agree this may be confusing. The fact is that probably because of how the training set was designed, there were, remember at the beginning of the course I said, water is a special case. Water is a special case. Water is a special case because it destroys the relationship between reflected and absorbed radiation, right? Any other type of length cover works fine, but water destroys our initial assumption that whatever is not reflected is absorbed. And this is a problem in many respects. One of the problems that this generates is the fact that water being transparent, its response is not homogeneous across the entire scene, but its response depends from if it's shallow, it depends from the underlying layer from the bottom of the water body. If it's deep, then it depends on the suspended matter. So my estimate is the reason why you find water here and there is because these are different types of water, in the sense that it's always water, but probably in one case it was a river water, in the other case was a pond or whatever. So different responses due to the fact that the environmental conditions, the local environmental conditions, led to having different responses. Okay, but it's not, mind that it's not infrequent that you have multiple decisions leading to the same land cover class. Why? Why? Let me ask you. For example, think of the maximum likelihood. What is the big advantage of this approach with respect to maximum likelihood? What do you need to make sure before you can use a maximum likelihood classifier? Gaussian, the Gaussian behavior. As I said, the Gaussian behavior is very nice. Frequently, it's a good representation of how things go, but it's not always the best choice. Okay? Why is it not the best choice? Because there exists land cover, especially if you're putting different things into the same basket, where the Gaussian will not describe it correctly. For example, vegetation. One thing that I did not mention, but it's time to pick it up. Vegetation does not respond all in the same manner. One of the main points of spectral response of vegetation is that obviously you have near infrared, a peak of reflection, of reflectance in the near infrared band. But that reflectance peak is very different for broadleaf vegetation and coniferous vegetation. So, for example, if you have pines, the pines will have a much lower infrared reflectance peak than broadleaves. So this means that you expect one Gaussian behavior on the infrared, but you actually have two. Coniferous plus and minus error, broadleaf plus or minus error. You cannot accurately describe a situation like this with a single Gaussian. You're making mistakes. Taking one average, the other average, you average them because you're averaging everything, and you get a Gaussian which is in between, and it describes well neither one nor the other. Okay? So we didn't touch on this, but there are other examples. When the classes that you're trying to discriminate do not have a Gaussian behavior, then you're stuck with maximum likelihood. In other respects, it's a fantastic classifier, but if you have these classes like this, it's bad. So what you see here is the reaction of the decision tree to the fact that the training made it to realize that actually this class is not just here, it is also there, and it is also there. So I cannot use a single descriptor. I will have multiple options, and I want to capture them all. And this results into a tortuous path to classifying the same land cover with different defining differences. Okay, does that make sense? This is something that you cannot do with the maximum likelihood classifier, and it is the essence of learning. When you call this machine learning, that's what we mean. The training phase has learned that such class could not be accurately represented in one single summary. Okay. Then decision trees are very intuitive and easy to explain. We have seen that. You look at the tree, and as I said, if you know how spectral behavior behaves, then you can explain why it proposes certain decisions. And yeah, but it also has its cons, which is it tends to overfit. Since it's so capable of adapting to the specific data set. So for maximum likelihood, there's no overfitting. There's no learning, so there's no overfitting. In this case, you may end up overfitting. So the classical countermeasure is using random forest, which I believe you know of. No? I think so. I mean, I think you know. Yeah. It's basically random forest can be explained very quickly. Random forest means generating a forest is many trees. A random forest is a number of different trees that were generated by tweaking a little bit the learning process so that every tree is slightly different from the others. So every tree may have captured a little clue that may have been missed by the others. And so when you average the response, you should be able to get a very good quality classification. And that's actually the case. I understand, and the experiments that I have made in the past confirm this, that a random tree, if you want to do a plain classification based on standard data, standard multispectral data, the random forests are the best. I mean, not always, obviously. Depends also on the data. But if you don't want to go crazy selecting a very specific, fancy, hyper good classifier, then the random forest is a very good choice. Okay, without much brain expense, you can be sure that you will get a decent or good result. Okay, then there are, I think I can skip the generation of random forest. I don't think you're interested in this sort of stuff. Not really like in any other case, the number of trees that you place in the forest determine how well the system is learning the features of the data, okay? In that if you have a few trees, you don't have many opportunities to capture the small clues that distinguish one class from the other. If you add trees, you can drag down the classification errors, but after a certain point, you add more trees, and these simply learn the same thing over and again, okay? Up to overfitting, okay? Yeah, we have already discussed this. Random forests have an effective approach for line-cover classification. Then the other classical machine learning approach is support vector machine. This is used in many, just like random forest, it's used across several disciplines. It's also used in remote sensing. It's basically, the idea is somehow similar to that of the random tree in that you have a decision surface separating the samples, and you have an algorithm that decides the optimal decision surface by looking at what is the distance between the decision boundary and the samples from each class that you're trying to separate. Okay. The problem with this classifier is that it assumes, so this is a step back with respect to random forest, in my opinion, in that when you use an SVM, you're basically assuming that in the space you have all the samples on one side, whereas the behavior may be more mixed. So when you have a situation where a line, like in this case, a line cannot separate the samples of one class from the samples of the other class, what you can do is you reproject the data into a different space where the two data sets become separable. This is done also in Earth observation. And even in this case, you can do this operation by applying some standard procedures. If you know what classes you're searching for and you analyze the data, you can also find smarter ways of addressing the problem, finding the transformation which fits exactly your data set. But I know that there are also deep learning approaches to this. So you give to the machine the pattern of training set data, and then you tell the machine how it should be transformed for optimal separation, and it learns how to separate them. Okay. Then there's the next step, which is deep learning. Like everywhere, remote sensing also embraced deep learning, including for classification. Okay? And so we have a number of algorithms that were developed also in other contexts, which are brought into the context of remote sensing and which work nicely. But you should also be aware that whenever you switch from machine learning to deep learning, you are somehow, to some extent, you need to take into account the increased computational demand of deep learning. Okay, even random forests require a lot of comparisons and a lot of operations, but they're still quite fast. But when you move to deep learning, which basically means introducing into the process elements which resemble the human neuron, okay, then you are implicitly taking on board a lot of computational requirements because these objects need a lot of computation, a lot of operations to complete their task. And this is one problem. The other big issue with deep learning is that you need, as you know, you need a lot of training data. And if the training data is too few, then it doesn't work properly. Okay. Let me see. So when you move from machine learning to deep learning, you introduce a neural network. You introduce neurons and you introduce a neural network classifier. The way it generally works is that, remember, the expected input is a vector or a matrix. Okay, and even in this case, you have a bar of neurons where you send in the elements of the input. And this is what we discussed earlier, a vector that conveys the information. What is this vector? It can be the spectral bands, for example. Okay. And then these spectral bands are processed here in the network with the neurons which combine these inputs with weights that are incrementally adjusted. And then, generally, when you have a classification, it means that you have an output layer composed of as many neurons as the classes that you are trying to distinguish. So that, based on the level of excitation of each of those neurons, there will be generally one which gives an output far higher than the others, and that basically defines the class that the network believes it has identified. Okay, and the network automatically learns the spectral features of the targets that you are trying to identify. And one specific type of neural network which is used also in Earth observation are the so-called convolutional neural networks, which is a combination of local convolution and then neural network, local convolution and then neural network, where you see, because this is, I think this is a question which is worth asking here. What you do here is you have a sliding window, and for every location of the sliding window, here you compute a feature map by convolving that portion of the image with a function which is defined for that specific classifier. You have multiple functions, so you have multiple feature maps. And then you throw away some of the samples, you do the so-called subsampling, and you get to this point, where you have further convolutions, etc. When you do a convolution, spatial convolution, what type of information are you collecting from the data set? Yes, you're collecting features, but what is the, can I say, how can I call this type of information? What am I pouring into the classifier? What type of information? Yes, but what type of information? Not intensity. So I agree with you, but the intensities, are what you're using. But what is the type of information that you're sourcing here from the image? No. You're doing a convolution. So you're taking into account the location of the pixels. Spatial information, yes. The CNN is particularly successful, especially in computer vision, but it is also used in remote sensing because it can source from the data set both spectral and spatial information. You can source both, because if you build this network in a manner which is suitable for a multispectral data set, you can take spectral features from every single band, and that's spectral information, because you look at multiple bands, and inside each band you look at each neighborhood, and you convolve the neighborhood with the function, and in that case you're collecting spatial information. Does that make sense? So this is a particularly successful type of network. Probably in the next lectures you will see it more in detail. I don't want to take too much of your time on this because this is the subject of the following lectures. I wanted to instead say a couple of things about contextual classification. What is contextual classification? Contextual classification means that you're considering more than one classification item at a time. So this means that, let me put it in another way. The classification process that I have described so far assumes that you pick up one sample at a time, you classify it, and you put it in the classification map. Then, if you decide, this works well if the individual element contains enough information for you to confidently classify it. So for example, if the spectral response is sufficient to separate it, if you're doing a simple task like separating vegetation from bare soil or vegetation from urban or whatever, then the spectral responses are different. And the simple spectral information that you see in the individual pixel is sufficient for you to say whether this is vegetation or bare soil or whatever. In other cases, this is not possible. One classical example is when you use radar data. We have discussed this already briefly in the first hour. When you have to do with radar data, you cannot rely on the single pixel. You may have speckle phenomena which make your single classification element, which makes the radiometry of the single classification element completely unreliable. So in this case, you need to look at the neighborhood. Okay, and that can be termed in two ways. You can say that you are using spatial information, as we did earlier this morning, or you can also say you're using so-called contextual classification. What does it mean? That you don't look at the simple pixel, at that one pixel that you are using that you're trying to classify in that moment, but you're also looking at the neighboring pixels. This is context, but this is somehow an ambiguous example. So let me give you a better example. This is the definition. Like, okay, I'm classifying this, but at the same time I look at this, and this, and this, and this, because they will support my decision. They will help me understanding what is located here. An example of case where context may be used is after a classification. So something which is frequently done in the use of context is after you do the classification process until the end, and then when you're done with the standard classification process, you apply a mask to each pixel, and you compare the class of that pixel with the class of the surrounding pixels. If that pixel is the only one of a different class and all the others are of the same class, different from that, then you simply turn that pixel into the same class. So you basically fill in the holes. Okay. That is a way of using context, not directly in the classification process, but afterwards. And this is something which is frequently effective in improving the results of classification. Let me give you another example where this is a building in our campus. I use this image because this is from year 2002. I remember we paid a lot of money for that. It was one of the first ever very high resolution images that I ever saw. And I remember it cost us a lot of money to purchase this image. There was no Google Earth at that time, but even if there was Google Earth, as I said, Google Earth gives you low quality images, not spectral responses. Okay, so we had this image here, and it is an example that I frequently cite to my students because this building is covered in asphalt, just like the roads which surround it. So if you want to use the terms that I defined this morning, what we can say here is that we have the same spectral class, right? So the spectral class of the building is the same as the spectral class of the roads. If you try to directly classify based on spectral information, you don't go far. This is class A, this is class A. Spectral class A, spectral class A. No way you can separate them using spectral information. So what are you supposed to do? Well, one thing you can do, obviously, you can leverage spatial information. But even spatial information is not very favorable here because, I mean, in terms, if you look at the immediate neighborhood of each pixel, it doesn't change that much. Okay, so there's little spatial information that you can leverage to do that. Spatial information is more effective if you have, for example, vegetation, but cultivated vegetation, which is very orderly, and natural vegetation, which is more messy. Then spatial information will help you because the relationships between neighboring pixels are different. Here it doesn't work. So you can use another type of spectral, of contextual classification. So you let alone spatial information, and you use contextual classification. Say, okay, this is this is asphalt, but there's a shadow next to it. There's a class shadow, pixels of class shadow next to it. A road has no shadows. And its context, it's a broader definition of spatial information, much broader. I look at the context, and I can tell this is a building, this is a building, this is a building, because they are next to a shadow. But then the road is a road, despite having the same spectral response, because the context tells me that this is a road. Okay. Do I still have time? Okay, because I wanted to say a couple of things before closing. A few words about the assessment of results. I said at the beginning, because I wanted to point out a couple of things. Probably you already know about accuracy, classification accuracy, right? You have a training set and you have a test set, and you use the training set to train the classifier, use the test set to assess the quality of results. Okay. Does this make sense to you? I don't need to go through all of it again. Okay. What can I tell you about this is that all this mechanism is necessary in remote sensing because, as I said, you should expect to have errors. Okay. The classification process is cheap, but on the other hand, it is far from perfect. Even if you use a state-of-the-art classification process, you should always expect errors. So accuracies over 90–95% are good accuracies. Okay. So how do you do that? You build the confusion matrix, which you should know how to do, and you get the count of correctly classified pixels, and you get the errors. And one thing I wanted to point out here is that the overall accuracy, namely how many elements are correctly classified versus how many elements are classified in general, is not extremely informative in all cases, because if you have an unbalanced distribution of classes, the overall accuracy will not be very representative. So you will have to resort to the so-called K coefficient, which tells you not how well you did in an absolute sense, but it will tell you how better you did, how better the classifier did with respect to pure chance. Let me put it in another way. If you have, suppose you're classifying an area where most of the pixels are vegetation, and then you have 3 or 4 buildings here and there, and you want to come up with a land cover map of this area. Okay. Suppose you have a multispectral or an hyperspectral acquisition, and you can use that hyperspectral acquisition to classify using whatever method you want to use. You get a map, and you assess the accuracy. Now, I want to do the whole thing much simpler. I ignore the data completely. I don't even purchase it, so I save money. I tell you that 100% of the pixels are vegetation. And if you compute the overall accuracy, it's going to be something like 99.9%. Why? Because there are so few pixels of the class building that if I ignore them completely, I will still get a very good accuracy. Okay. Sorry? Yeah, but I tend to be wary of overall accuracies that are extremely high, because when you have accuracies close to 100%, you may have done very well, or you may have missed something. Okay, so this is what I wanted to point out. Overall accuracy is a good measure, but it may not be always saying the whole story. This is why they invented the K-hat coefficient. So my suggestion is when you assess a classification result, you use also the K coefficient. And I can also add that actually when you do an operation like what I described, so when you want to identify very few pixels on a background which is uninteresting, that's called a target identification problem. It's not a general land cover classification problem. It's a category in itself. Obviously, it's a part of a land cover classification problem, but it follows, if you want to make the most of it, you should call it by its name, which is target detection process, which means that you will also assess the accuracy not based on the confusion matrix, which won't help you, but based on, for example, the IOU, so intersection over union of pixels detected as building with test set. That will be a much more convincing assessment of your of how well the classifier did. Okay, so I think we could stop here at the moment. And thank you again. And then I will, after the break, I will leave the floor to my dear friend, Professor Lal. Welcome, Professor Lal.
Nice to meet you. Yes, yes, yes.
So nice to see you. Okay. Okay, so now let's take a break and we will reconvene here in about a quarter of an hour. It's 12:15. Yeah, 10 minutes, let's say. I